Welcome to the session on linear models. We will be studying the simple linear regression, estimation of model parameters, properties of estimates, estimation of error variance, hypothesis testing in the simple linear regression model, interval estimation in simple linear regression model. Now, what is basically a model? As we can see at one glance that this is a model of the solar system. This represents some phenomena. This is an example of a scaled down version of an iconic or physical model. Such models are easy to construct and understand, but they serve no purpose for forecasting purposes or estimation purposes. Mathematical or statistical models often describe relationship between variables and are broadly classified as deterministic models where there is no randomness, or probabilistic models where there is some stochastic nature or randomness involved. Deterministic or predictive models hypothesize the exact relationships. They are suitable for use when the prediction error is negligible. For example, the period of oscillation of a simple pendulum depends on its length and the acceleration due to gravity. That is, we have the formula t is equal to 2 pi under root L by g. So if I want to calculate t, the period of oscillation, then for fixed L, everybody will get the same answer. G is a constant, 9.8 meter per second square. As another example, let us consider the body mass index, which is an anthropometric index of body fat defined as the ratio between weight in kg divided to the square root of height in meters. At constant temperature and volume, the pressure of a gas is directly proportional to the number of moles of gas, that is PV is equal to nRT. So again, all these are examples of deterministic or predictive models. Probabilistic models. So there are two components, deterministic or assignable components, which we can study and eliminate, and the chance or random error component, which cannot be studied or eliminated as it is inherent in the setup that we are investigating. For example, the systolic blood pressure of newborns is 6 times the age in days plus random error. So we postulated the model as 6 times age plus error. Random error may be due to factors other than age in days. For example, the birth weight, weight on the day of measurement, arm circumference, etc. So all these are beyond our control. We cannot control all this. So this will be clubbed in random error component. Regression analyses. The term regression literally means stepping back towards the average. It was first used by Galton while dealing with the inheritance of stature, as he found out that offsprings of abnormally tall or short parents tends to step back or regress towards the average population height. As of now, it is defined as a mathematical measure of the average relationship between two or more variables in terms of the original units of the data. Regression models the relationship between one dependent variable and one or more explanatory variable. It uses equation to set up the relationships dependent response variable and with one or more independent or explanatory variables. Now, explanatory variables can be numerical or categorical, while dependent variable is numerical. It is used mainly for prediction and for estimation. Regression modeling. So step 1, hypothesize the deterministic component. Step 2, specify the probability distribution of the random error term. Step 3, estimate the unknown parameter or parameters. Then estimate the standard deviation of error. Obtain the fitted model. Use the fitted model for prediction and estimation. The deterministic component. Define the dependent variable and independent variable or variables. Hypothesize the nature of relationship between the expected effects, the coefficient signs, that is synergism or antagonism, whether you expect positive relationship or negative relationship, the functional form, whether you are considering a linear or a non-linear model, interactions, whether they are significant or can be neglected. They are negligible or not. Model specification requires knowledge about the field of application, mathematical theory, previous research if it is available, and practicality of the model is important. That means your model should be feasible. Now, types of regression models, depending upon one explanatory variable. If there is only one explanatory variable, then the regression model is called simple. And if there are more than one explanatory variables, then regression model is called multiple. Now, depending upon the relationship of the parameters, whether the parameters are linear or quadratic and so on and so forth. So, depending upon the type of parameters, you have simple linear regression model. Similarly, non-linear, when the parameter to be estimated is not linear, then this becomes non-linear simple regression model. When we have more than one explanatory variables, when it is linear in the parameters to be estimated, we have linear, multiple, more than one regressor variable, and non-linear, the parameters to be estimated are not linear. Now this is an equation of a straight line, y is equal to mx plus b. B denotes the y-intercept and m is the slope, which depicts the change in the mean of the distribution of y produced by a unit change in x. If the range of the data on x includes x equal to 0, then the intercept b is the response y when x is equal to 0. Otherwise, b has no practical interpretation. Population linear regression model, yi is equal to beta naught, where yi denotes the ith dependent or response variable, is equal to the population y-intercept beta naught plus the product of beta 1 with xi. Xi denotes the ith explanatory variable. Beta 1 is the population slope plus the random error. Now the problem is that we have a population and we have a problem at hand. We are supposed to obtain the estimates of the population parameters. Now population is the entire units, all the units that we are considering for estimation purposes. So due to constraints of time and money, we do not resort to complete enumeration. Sometimes if the testing is destructive, like if we are testing the breaking strength of chalks, or we are trying to estimate the length of life of a tube light or LED and so on, so testing is destructive. By the end of the testing, we will not be left with any of the units. So in this case, complete enumeration is possible but not at all advisable, because by the end of the experiment, we will not be left with any of the units. So in such cases, a way out is provided by sampling. We are supposed to choose a sample which is representative of the entire population. We should avoid choosing contiguous units. A way out, a way to choose a random sample is either you can use Tippett's random number tables and choose your sample units depending on the sample size by a draw of lots, or you can choose a simple random sample or systematic sample in which you choose every ith unit and so on and so forth. Subjective or biased sampling should be avoided as it will not give us reliable estimates. So on the basis of the sample estimates, we try to obtain the parameter estimates. So here we have a population linear regression model. This is the observed value. For a particular I, yi is beta naught plus beta 1 xi plus epsilon I. This is the fitted line of regression. Expected y is beta naught plus beta 1 xi, and these are observed values. Sample linear regression model. So some of the observations are unsampled. They are not being included in our sample, and this denotes the deviation epsilon I between the fitted line and the yi value. So way out is to plot the data, xi, yi data, and then we have to determine the line of best fit. Now, for example, if we have our data like this, then here slope is unchanged, intercept is changed. We can make such a line. The same set of data we can have something like this. Slope is changed but intercept is changed. Now which is the line of best fit? That is the problem. Let us move on to simple linear regression. So as we have discussed earlier, simple linear regression means that we have two terms. Simple linear regression, we have already discussed what it means. So linear in the parameters to be estimated. So what are the two parameters here? Beta naught and beta 1. So this is a linear model. Simple if there is only one regressor variable. So here we just have x. So this is a typical example of a simple linear regression model. Let us consider models 1.2 through model 1.5. So here let us see whether this is an example of simple linear regression model or not. So please jot down in your copies what you think about these models, whether they are simple linear or not, and let us check out. Now for the first model, y is equal to beta naught plus beta 1 x square plus epsilon. So simple means that there is only one linear regressor, one regressor. So here you have x square. So you might think that the surface generated is quadratic, so this is not linear. But linear, we have to check out the powers of beta naught, beta 1, what surface beta naught and beta 1 are having. So beta naught is linear, beta 1 is linear, so this is linear. X square I can redefine as x1. So this will become y is equal to beta naught plus beta 1 x1 plus epsilon. So same as this, x1 is x. So this is an example of a simple linear regression model. How about model 1.3? So log beta 1. So this is not linear. X square I can redefine as x1. So this is simple, only one regressor variable. This is an example of a simple non-linear regression. Beta naught power 4. So here beta naught beta square, so this is non-linear. X power 6. So again I can redefine. So this is an example of a non-linear simple regression model. So beta naught q plus beta 1 x square plus epsilon. So you can do it yourself. Estimation of intercept beta naught and slope beta 1. We assume for such investigations that the data is available for n pairs such as xi, yi for all I going from 1 to n. Sample regression model is yi is equal to beta naught plus beta 1 xi plus epsilon. The assumptions underlying model 1.6 are that expected value of the error term is 0, that is the error term has mean 0 for all I, implying that expected yi is equal to beta naught plus beta 1 xi for all I varying from 1 to n. Epsilon i's are independently distributed, implying that expected epsilon I epsilon j equal to 0 for all I not equal to j, covariance is 0 and variance is equal to expected epsilon I square is equal to sigma square for all I, that is we have the assumption of homoscedasticity. Variance of yi is constant equal to sigma square for all I going from 1 to n. The method of least squares does not require any assumptions regarding the distribution of xi by I going from 1 to n. According to this method, the error sum of squares is minimized with respect to the unknown parameters. In other words, the estimators beta naught hat and beta 1 hat are obtained such that the sum of the deviations yi hat from yi are minimized, where yi hat denotes the predicted or fitted model given in equation 1.7. The difference between yi hat and yi is called a residual. In particular, epsilon I denotes the ith residual given in equation 1.8 and constitutes that part of the dependent variable not explained or predicted from the independent variable. The adequacy of the fitted regression model is checked using residual analysis. Residuals also help in checking the validity of the assumptions underlying the model. So ith residual is the deviation, yi minus yi hat. Best fit means that the difference between actual y values and the predicted y values are a minimum. The method of least squares minimizes the sum of the square differences, SSE. Now least squares explained graphically. Least square is equal to summation this. So y2 for the second variable is beta naught plus beta 1 hat x2 plus epsilon 2. So we have the deviations epsilon 1 hat, epsilon 2 hat, epsilon 3 hat, epsilon 4 hat, and this is our y. The least square criteria. So according to the principle of least squares, we minimize the sum of squares due to error, SSE, or sometimes denoted by S beta naught beta 1 equal to summation of yi minus beta naught minus beta 1 xi square. So we differentiate partially with respect to the unknown constants and equate to 0 at the values beta naught hat and beta 1 hat. So we obtain the first derivative equate to 0. Similarly, with respect to beta 1, and b equal to 0, we obtain two normal equations. One is n beta naught hat plus beta 1 hat summation xi equals summation yi, and beta naught hat summation xi plus beta 1 hat summation xi square equals summation xi yi. Now these are two equations in two unknowns. We can solve them uniquely to obtain those estimates of beta naught hat and beta 1 hat. So either we can multiply the first equation by summation xi throughout and the second equation by n and eliminate beta naught hat to obtain the estimate of beta 1 hat equal to this, and which can be represented as this. And then dividing by n this equation, first normal equation by n, we can obtain beta naught hat is equal to y bar minus beta 1 hat x bar, where y bar denotes the sample mean of y observations and x bar denotes the sample mean of x observations. Prediction equation is given by y hat is equal to beta naught hat plus beta 1 hat xi. Sample slope beta 1 hat is equal to ssxy upon ssxx given by this expression. Estimated y changes by beta 1 hat for each 1 unit increase in x. Example, if beta 1 hat is 2, then y is expected to increase by 2 for each 1 unit increase in x. Sample y-intercept beta naught hat is given by y bar minus beta 1 hat x bar. Average y value of y or average y value when x equal to 0. If beta naught hat is equal to 4, for example, then average y is expected to be 4 when x is 0. Example 1. Fit a simple linear regression model to the following data. Also show that the sum of residuals is 0. So you can solve and then check your answers. So fitted model is coming out to be this. And you have to check whether epsilon I is 0 or not. You're supposed to calculate y hat and epsilon I hat and then check your result with this table. The properties of least square estimate. Sxx is equal to summation xi minus x bar square. Sxy is summation xi y minus summation yi summation xi by n, which can be expressed as this. And beta 1 hat is beta sx upon sxx. So expected value of beta 1 hat comes out to be equal to beta 1. Expected beta naught hat is equal to beta naught, and expected yi is beta naught plus beta 1 x. So beta 1 hat is unbiased for beta 1, and similarly beta naught hat is unbiased for beta naught. Variance of beta 1 hat is sigma square summation ci square, with this term is equal to xi minus x bar square. So this is sxx and this is s square xxx. So one of them is getting cancelled. Variance beta 1 hat is sigma square by sxx. Similarly, variance of beta naught hat, we have taken the term variance for this beta naught hat. So variance of y bar plus x bar square, since x bar is a constant. Variance beta 1 hat minus twice x bar for variance of y bar beta 1 hat. Now this term is 0. So variance beta naught hat is variance of y bar, which is equal to sigma square by n plus x square times variance of beta 1 hat, which is sigma square by sxx. From here we are getting SSE sum squares due to error is equal to summation y minus y hat square. SSE is summation yi square minus n y bar square minus beta 1 hat sxy on using equation 1.7. Or summation y minus ny bar square is equal to sy by, which denotes the corrected sum of squares of observations. Sum squares due to error can also be expressed as sy by minus beta 1 hat sxy. This has n minus 2 degrees of freedom, because the degrees of freedom is defined as the total number of observations minus the number of linear independent constraints imposed on them. So number of constraints, 2 constraints are imposed since we are obtaining the estimates of beta naught and beta 1. Sigma hat square is SSE by n minus 2 is equal to MSE. This estimate of variance is model dependent because we have assumed that error terms follow normal distribution with mean 0 and variance sigma square. So estimate sigma square for the data given in example 1. Transformed linear regression model. For simplicity, we can write yi is equal to beta naught dash plus beta 1 times xi minus x bar plus epsilon I, where beta naught dash is beta naught plus beta 1 x bar. Now sum of squares due to error SSE is summation I square is equal to this yi minus the estimated value The least square estimates of beta naught and beta 1, say beta naught hat and beta 1 hat, must satisfy. So this should be beta naught dash, dash is missing, must satisfy that the partial order derivatives with respect to beta naught hat dash and beta 1 hat is 0. Now del SSE by beta naught hat dash is 0 implies that this is equal to 0. So we have differentiated this partially with respect to beta naught. So minus twice of this term. Similarly, we will obtain. So this normal equation will yield summation y's and beta naught hat dash, or beta naught hat dash is y bar, since some deviations from the arithmetic mean is 0. Also, partial derivative of sum of squares due to error with respect to beta 1 hat equating to 0 yields this term. So this beta 1 hat we have taken. So this product will come outside, minus 2 equating to 0 implies summation xi minus x bar y minus y bar equals beta 1 hat summation xi minus x bar square using beta naught hat dash. The estimate of this is y bar. So we have replaced beta naught hat dash by y bar here. So beta 1 hat is equal to sxy over sxx. The fitted transform linear model becomes y hat is equal to y bar plus beta 1 hat x minus x bar. Example 2, fit the model yi is equal to beta naught dash plus beta 1 xi minus x bar plus epsilon I, where beta naught dash is equal to beta naught plus beta 1 x bar to the set of data given in example 1. And then you can check whether you've got the correct answers or not. Properties of intercept and slope for the modified model. Beta naught hat dash is unbiased for beta naught dash. For the model yi is equal to beta naught dash plus beta 1 xi minus x bar plus epsilon I. If we take expectation on both sides here, we have expected beta naught hat dash is expected y bar is expected value of this term. This is equal to 1 by n. So beta naught dash is constant plus beta 1 expected value of xi minus x bar plus expected value of the error term, implying that expected beta naught hat dash is equal to beta naught dash, as expected value sum of deviations of a set of values from the arithmetic mean is 0 and error terms have been assumed to have mean 0. So variance of beta naught hat dash is sigma square by n. We are supposed to prove this. So let us see, variance beta naught hat dash is equal to variance y bar. So we have taken variance. Beta naught hat dash is equal to this term. So variance of a constant times this. So n square variance becomes this. So variance of summation epsilon I, as beta naught dash and beta 1 are parameters, that means they are constants, and xi minus x bar is constant for all I. So only epsilon I will be counted here. All other terms will have variance 0. So variance of beta naught hat dash is equal to 1 by n square variance of summation epsilon I plus twice summation I naught equal to j covariance epsilon I epsilon j. So variance of 1 by n square, this is expected value of epsilon I square, since error terms have covariance is 0 and expected of epsilon I is 0, so only this term will come. As variance epsilon I square is expected epsilon I square is sigma square and covariance are 0. This implies that variance of beta naught hat dash is equal to sigma square by n. Example 3, show that beta naught hat is unbiased for beta naught and hence find its variance. So there is another way using the transformed model. We know that beta naught is equal to this term, beta naught hat. So we will take estimates is equal to beta naught hat dash minus beta 1 hat x bar. Take expectation on both sides. Expected beta naught hat is equal to expected beta naught hat dash minus expected beta 1 hat x bar. So expected a minus b is equal to expected of a minus expected of b. So we have taken x bar outside. This is a constant. Expected beta naught hat dash is equal to beta naught dash. We have proved that beta naught hat is unbiased for beta naught dash. Expected beta naught hat dash. So this is equal to beta naught dash minus x bar beta 1. Beta 1 hat is unbiased for beta 1 and beta naught hat dash is unbiased for beta naught dash. So this is equal to beta naught from here. So beta naught hat is unbiased for beta naught. Also variance of beta naught hat is given by variance of beta naught hat dash minus beta 1 hat x bar. So this is equal to variance a minus b is equal to variance of a plus variance of b minus twice covariance a. So variance beta naught hat dash is y bar x square, x is a constant, so x square outside the variance term, beta 1 hat minus 2x bar, so this is coming out, covariance of beta naught hat dash beta 1 hat. And this term is 0, so this is equal to variance of pi bar is sigma squared by n, x square constant as it is, variance of beta 1 hat is sigma squared by sxx. Hypothesis testing on the slope h naught beta 1 equal to beta 1 naught against the alternative, which is two-tailed, beta 1 not equal to beta 1 0. We assume the error terms to follow normal distribution with mean 0 and variance sigma square. This implies that yi follows NID, beta naught plus beta 1 xi being the mean and constant variance sigma square. This implies that beta 1 hat follows normal distribution with mean beta 1 and variance sigma square by sxx. Now, depending upon whether sigma square is known or not, we have two cases. Now, case 1, if sigma square is known, then the z statistic under h naught z naught equal to beta 1 hat minus beta 1 naught divided by the standard error follows normal distribution, standard normal distribution. Now, case 2, if sigma square is unknown, then test statistic under h naught t naught is equal to beta 1 hat minus beta 1 naught divided by square root of MSE by sxx follows t distribution with n minus 2 degrees of freedom. Now, we may reject h naught if the absolute value of t naught exceeds the tabulated value alpha by 2 n minus 2. Since it is two-tailed, we have taken alpha by 2 at alpha percent level of significance. Otherwise, we may retain the null hypothesis. Hypothesis testing on the intercept. To test the null hypothesis, beta naught equals some constant beta naught naught versus h1 beta naught not equal to beta naught naught. So again, two-tailed alternative. So test statistic under h naught, t naught is equal to beta naught hat minus beta naught naught about divided by under root of MSC 1 by n plus x bar square by sxx. This follows t distribution with n minus 2. So reject h naught if t naught absolute value exceeds the tabulated value t alpha by 2 n minus 2. Then sigma square is not known. Now test for significance of regression. To test the null hypothesis beta 1 is equal to 0 against the alternative beta 1 is not equal to 0. Failing to reject the null hypothesis implies that either x is of little value in explaining variations in y, or there is no linear relationship between x and y. So we have situations where h naught is rejected. So we are rejecting h naught if these situations are arising. Situations where h naught is rejected. Situations where h naught is not rejected. So if we have beta 1 equal to 0, and here we are having beta 1 not equal to 0. So this figure says that x explains the variability in y. So either a straight line model is adequate from this figure, or from here we may infer that better results may be obtained by adding higher order polynomials in x. Test procedure 1. So to test h naught beta 1 is 0, there are two ways. One is that we can represent y minus y bar as sum of two quantities by adding and subtracting y hat. On summing and squaring this, summation y minus y bar square is equal to summing and then squaring. So a square plus b square, a square plus b square plus 2ab. So we can open summation y hat minus y bar into y minus y hat and write these two expressions. Now sum of errors summation I is 0. Also the sum of errors weighted by yi hat is also 0. So we are left with summation y minus y bar square is equal to summation yi hat minus y bar square plus summation y minus yi hat square is equal to syy. Sum of squares due to error or residual sums of squares is this we have discussed. Sum of squares due to regression is summation yi hat minus y bar whole square. That is syy can be expressed as sum of two non-negative quantities SSR plus SSE. Also sum of squares due to residual is syy minus beta 1 hat sxy. So SSR is nothing but beta 1 hat sxy. To test h naught beta 1 equal to 0, analysis of variance is used. So this is the ANOVA table. We have the sources of variation, regression, residual, total. Sum of squares is SSR, which is equal to beta 1 hat SXY. Sum of squares due to error and sum of squares TSS. Degrees of freedom 1, because here we have beta 1 hat. N minus 2 are the degrees of freedom for the residual, and total is N minus 1, because total number of observations is N and only one constraint we are imposing for the total. That is summation y minus y bar is 0. So mean square is MSR is SSR divided by degrees of freedom. Mean square error MSE is SSE divided by N minus 2. Variance ratio or F is given by the ratio of MSR by MSE, and this follows F statistic with 1 and N minus 2 degrees of freedom. Now we will reject H0, or we may reject H0 if the calculated value of F exceeds the tabulated value at alpha and 1 and N minus 2 degrees of freedom. Otherwise, we may retain H0 beta 1 is equal to 0. Another way to test H0 beta 1 is equal to 0 is by using the t-test, defined as this ratio beta 1 hat by the square root of MSE by SXX. Squaring both the sides, t0 square is beta 1 hat square SX divided by MSE is equal to beta 1 hat SXY by MSE is equal to MSR by MSE. So this is beta 1 hat square. So beta 1 hat. T0 square is identical to F0. So both the tests are identical. Now the choice depends upon whether you need to test for two-tailed alternative, because F is giving you a two-sided test or two-tailed alternative, whereas for t-test it is offering more flexibility in the sense that you can test both the right-tailed alternative or the left-tailed alternative in your alternative hypothesis. For example, for some data, this is given to us, N is 20, Y height is also postulated, is given to us, this is all calculated. So you are supposed to carry out your ANOVA test and check whether this is true or not, that T0 square is equal to F0. So you are supposed to calculate your F statistic and then check whether T0 square equals the F statistic or not. So whether both the procedures give identical results or not. Now 101 minus alpha % confidence interval on the slope beta 1. So beta 1 hat minus beta 1 divided by square root of MSE follows t distribution with N minus 2. So you have your fiducial limits as beta 1 hat minus t alpha by 2 N minus 2 under root of MSE by SXX, and then upper fiducial limit is beta 1 hat plus t alpha by 2 N minus 2 under root of MSE by SXX. Sometimes the problem arises that for the same confidence coefficient, several intervals are obtained. Then the problem is to choose which interval is the best, which provides the best estimate for the population parameter to lie. Because point estimates, they put forward a numerical quantity, and whereas interval estimates give us an interval within which the population parameter is expected to lie, and this may sound more appealing to some, that interval within which the population parameter is expected to lie. Then obviously we should choose that interval which is shortest in length, as it is most precise. Now 101 minus alpha % confidence interval on the intercept beta naught hat minus beta naught divided by square root of MSE 1 by n plus x bar square by SXX follows t with n minus 2 degrees of freedom. So here you have your lower fiducial limit and upper fiducial limit, between which beta naught lies. For example, construct 95% confidence interval for beta 1 if beta 1 hat is this, tabulated value is given, MSE is also given, then you just construct your confidence interval and check whether you are getting this or not. 101 minus alpha % confidence interval on sigma square is provided by lower fiducial limit is n minus 2 MSE by chi square alpha by 2 n minus 2, and upper is n minus 2 MSE by chi square 1 minus alpha by 2 n minus 2. These are the references. Thank you.